Hello, and welcome to Section 2.5 Continuity. In this section, we're going to be talking about a rigorous way to define functions as continuous or not. You're going to need to remember the limit laws that we learned in Section 2.3. We'll be seeing a lot of rational functions and wholes again, and piecewise functions again. So you'll recall from pre-calculus when you just looked at different types of functions, such as rational functions or certain trig functions, that graphs were not continuous. You talked about continuity in the sense of graphs, and it was kind of defined as, well, if you have to pick the pencil up off the paper when you're graphing, it's not continuous. So here's the tangent function, this dashed function, and you see that it's not continuous for where cosine x is 0, and that is going to be at odd multiples of pi over 2. So these are all different branches of tangent x that are not connected. And then this solid blue graph is 1 over x, so that's a rational function, and it's in two pieces. It's discontinuous at x equals 0. So we're going to see a rigorous definition as to why these functions aren't continuous. And we're going to be able to determine if a function is continuous just by the formula, not by looking at breaks in the graph. So the definition of continuity is based on limits. So a function is continuous at a number a in its domain if the limit as x approaches a of the function actually equals f of a. So it's implied that this limit exists and that f of a is defined. So if you think back to section 2.3 when we evaluated limits of polynomials and rational functions by direct substitution, that's why we could do that, because polynomials and rational functions are continuous at every point in their domain. So that's why we could just plug numbers into the function to find the limit. So there's different classifications of discontinuities. If you look at this rational function that we've looked at again and again, this whole at the point 1, 2, is an example of a removable discontinuity, because you can define this function to be defined when x is 1. I can define it to be defined as y is equal to 2 with a piecewise function, and then I've removed the whole. So I'm making a piecewise function out of it, which are handy things to use when you're talking about limits and continuity. And I've said, okay, when x is 1, just make y 2. And now that whole's gone. So that's an example of a removable discontinuity. It's just a whole. Here's an example of another type of continuity called a jump discontinuity. So this is the signum function. And notice it's really giving the sign of a function. of a number, its input. So it jumps from this horizontal line at y equals 1 down to the horizontal line at y equals minus 1. And even though it's defined at x equals 0, it's not equal to either one of these pieces, notice. But I can't redefine any one of these points and make it continuous. I still have these two separate branches. So this is called a jump discontinuity, but you can't remove it. So notice that the reason this guy is not continuous, not just looking at it graphically, but thinking about it algebraically, the limit does not exist at x equals 0. The limit from the left equals minus 1, but the limit from the right equals 1. So that limit doesn't exist, therefore it can't be continuous. And here's an example where I have an infinite discontinuity. So I have a vertical asymptote clearly I can't redefine any value of x to make it continuous. And the reason it's an infinite discontinuity is because it's an infinite limit. So there is the concept of one-sided continuity. That's where the limit from one side exists. So if a function continues from the right, the limit from the right exists and is equal to f of a. And likewise, if it's continuous from the left, the limit from the left exists and is equal to a. So if you look at this function, graphically, this is continuous from the right because the limit from the right as x approaches 0 is f of 0. But it's not continuous from the left because the limit from the left, notice, is minus 1 as x approaches 0, but f of 0 is 1, not minus 1. So there's also the concept of being continuous on an interval. So a function is continuous on an interval if it's continuous at every number in that interval. So here's a word example of this function defined on minus 1, 2, the x interval minus 1 to 2. So minus 1 is open. So this is, looking at the graph, it's clearly not continuous on this interval. The reason being there is this jump discontinuity here. So let's look at the rigorous reason why it's not continuous. So let's look at the endpoints. The limit as x approaches 2 from the left equals f of 2 because I have that filled in endpoint. So I can say this function is continuous on the interval 0, 2, where 0 is open and 2 is defined and included. If we look at this piece, this is also continuous from the left at 0 because as x approaches 0 from the left, the limit exists and is equal to f of 0. So this function's continuous on the interval open 0 to close 2, and it's continuous on the interval open minus 1 to close 0, but it's not continuous on the entire interval. So since continuity's definition is derived from limits, those laws of limits apply to continuous functions. So if you have two continuous functions, their sum and difference is a continuous function. I can multiply a continuous function by a constant, and that's still continuous. Their product and their quotient are continuous as long as the function g is not equal to 0 at a certain number. So remember all those functions that you covered in pre-calculus that are continuous in their domains. Polynomials and rational functions, root functions, trig functions, inverse trig functions, exponential functions, and logarithmic functions. They're continuous at every number in their domain. So again, we'll look at a piecewise function. Is this function continuous at x equals 0? Well, you need to check the endpoints of these domains defined in the piecewise function. So cosine of x is continuous everywhere, and 1 minus x squared is continuous everywhere. So let's look at what's happening. So as x is less than 0, and x is approaching 0 from the left, that means that the limit is going to be approaching 1. The y values will be approaching 1 because cosine of 0 is 1. However, the function definition at 0 is equal to 0, not 1. So this is discontinuous from the left. Now if you look at these two parts, as x is approaching 0 from the right, it's using this function, so it's approaching 1. However, x of 0 is not 1, it's 0. So it is not continuous at x equals 0. Let's look at this example, this rational function. Determine if it has any discontinuities, and if it does, classify them. Well, the first thing you're going to want to do is factor the numerator and denominator to see if you have any common factors, to see if you have any wholes. And then you want to look at the zeros of the denominator, if there are any others for this function. So when we factor the difference of two cubes in the numerator and the difference of two squares in the denominator, we see that x minus 2 is a factor that's common to both the numerator and denominator. So x equals 2 is a whole. So we have one removable discontinuity. And then x equals minus 2 is a 0 of the denominator we see from this factor. So that's going to be a vertical asymptote. So there's going to be a whole at x equals 2, which is removable. And there's going to be a vertical asymptote at x equals minus 2, which is an infinite discontinuity. So this theorem is telling us that the composition of two continuous functions is continuous. And you've actually seen that in section 2.3 when we were allowed to put the limit symbol inside of a function, if you recall. So let's take a look at this. This is a handy theorem. So we're going to use continuity to evaluate this limit. And we're going to use that theorem that we just saw, that the composition of two continuous functions is continuous. So let's look at the inside function of this composition. This is a rational function, and it's defined for all x, since x to the fourth is always positive. It's never going to be negative 1, so that we're never going to have a 0 in our denominator. And so we know it's continuous everywhere. Now the outside function is the square root of x, and we know that that's continuous for all x greater than 0. We can only put values of x greater than or equal to 0 in that. And notice also that this rational function is greater than or equal to 0 everywhere. So each of these functions, the inside function and the outside function, is continuous, so their composition is continuous everywhere. So that means that the limit as x approaches 1 of this function must actually equal f of 1, because that's the definition of continuity. So since we know it's continuous, we can evaluate the limit by just plugging in f of 1. We're plugging 1 into the function, and we get the square root of 1/2. There's the graph you can verify with. The intermediate value theorem isn't used a lot in your mainstream kind of problems. It's more the end of the section type problems. But the intermediate value theorem is really just telling us that we can pick, for a continuous function, it's going to take on all values of y in its domain. So if I have a function defined on let's say between minus 10 and 10. I'm using this function x cubed. I can take this horizontal line, and it's always going to intersect this function, which means that there's always a y value for any x value on this interval. There's not going to be any breaks in the function if it's continuous. Here's another example that I'll leave to you. With piecewise functions, you want to look at each individual function, and then you want to look at the endpoints to see if your limits work out from the right and the left. And I'm running out of time as usual with my videos, but the summary page can be left for you. Bye.